So we just talked about independent events. Now let's talk about dependent events. Events are dependent if they do affect each other. I should add the word they, I suppose. If they do affect each other. So for example, well, here's a visual for the example. If you have different fruit in a bag, you've got 2 lemons and 1 lime. So on your first draw, if you're just randomly choosing fruit, which I don't know why you're doing this, but anyways, if you're randomly choosing fruit from the bag, you have a 2/3 chance of drawing a lemon or a 1/3 chance of drawing a lime. Now, if you take the lemon out, now half the fruit left in the bag are lemons, and half the fruit left in the bag are limes. But if you draw a lime first, then you have no limes left. So there's a 0% chance that you're going to select 2 limes in a row. But if you select a lime first, then there's a 100% chance you're going to select a lemon because the only fruit left in there are lemons. So the first prime example is, well, this lemon and lime example. The other example, and this is referencing one that I mentioned on the previous one, so drawing a card and not replacing it. So if you take a card out, essentially if you remove an option from your probability, it is now a dependent event. So when calculating dependent events, we have to talk about this thing called conditional probability. Now, if you were in class, we talked about this a little bit in person already in section 7.2, but we're going to hammer this home right now. So to calculate dependent events, we use conditional probability. We read as P of the probability of B assuming A happened, or given that A happens. So we calculate the probability of B, and we have to do it based off of the fact that we know that A has already happened. So if A and B are dependent events, then the probability of A and B happening is the probability of A happening multiplied by the probability that B happens, assuming that A already happened. And so again, that last part says where P of B assuming A is the probability that B of B, given that A has already occurred. So let's talk about what this looks like. So 2 dice are rolled, 1 red and 1 blue. If you're using a paper copy, it's 1, well, to the left and to the right. We're asked to find the probability that the red cube shows a 6 and the sum is greater than 9. So I'm going to start off with just kind of that notation. So I'm going to say, what's the probability that we get a red 6 and the sum is greater than 9? So that the sum greater than 9 is going to kind of depend on what the first thing is. So we're going to do the probability that we draw that we roll a red 6 multiplied by the probability that your sum is greater than 9, assuming we already know that we have a red 6. Now, starting off with this, looking at this graph here, the red 6s, that's all these down here. There are 6 of them out of all 36 options. So we're going to say it's a 6 out of 36, or 1/6 chance. Now, the probability that the sum is greater than 9, assuming we already have a red 6, that means we're only really paying attention to, again, just these numbers down here. So of those numbers, 3 of these sets down here, so 3 of these sets down here have a sum greater than 6. So it's 3 out of, greater than 9, my apologies. So 3 out of the 6, in other words, half of those options. So when we multiply these together, we end up with 1/6 times 1, I'm just rewriting it. 1/6 times 1/2 gives us 1/12. Now, explaining why these events are dependent, making sure we're answering that full question, is because the red 6 reduces our options. Now, there is another way we can talk about this. Looking at this, in total, there are 3 total options out of the entire set of 36. So another way we could have approached this is said, oh, it's 3 out of 36, which is 1/12 as well. Let's take a look at one more example like this. So 2 dice are rolled again. One got a red and a blue, some left and right. Find the probability that the red shows a number greater than 4 and the sum is greater than 9. So we're going to do probability of red greater than 4 and the sum has to be greater than 9. So the red's greater than 4, that takes care of all of these. Let's just focus on that. So when we're calculating it, we're going to do the probability that a red is greater than 4. I missed the number there. So red greater than 4 times the probability that the sum is greater than 9, assuming we already have a red greater than 4. Now the red's greater than 4, I already circled those. There's a total of 12 of them out of 36, which can reduce to, well, maybe let's actually leave it as 12 out of 36 for a second. Now, of those 12, we're looking for which of those 12 have a sum greater than 9. Well, there's only a handful of them. The sum greater than 9, we've got this one here, so 5, 5, 5, 6, 6, 4, 6, 5, and 6, 6. So there's 12 of them total. So we end up with 12, sorry, there's 5 of them total out of those 12. So that's 5 out of 12. Now you notice in this case I didn't reduce them, and honestly sometimes it's kind of nice to not reduce. So we have 12 over 36 times 5 over 36. We could just multiply and do 12 times 5, which gives you 60, 36 times 12, which gives you, I'll be honest, I didn't prep this because I wasn't planning on doing that, because it's just way easier to reduce these fractions by cross-canceling. So we have 12 and the 12 cancel out, they each become 1s. So we have in our numerator now 1 times 5, which is 5, and then 36 times 1, which is 36. So the overall probability is 5 over 36. Now again, for why these events are dependent, the red greater than 4 reduces our options. Really, that's the general theme if you're looking for why things are dependent. If the first event reduces your total number of options, then you have a dependent event.